Okay, so let's move on. The next thing we have to take care of is our input parameters for our Grasshopper component. And we are going to define them with this register input parameters method. So basically, these are the parameters that we are getting with our template, and we are going to replace them. Like that. And the first thing we need to do is to use this kind of parameter manager object that we are specifying as an argument for this method. So now we can just write a point here, and we can see how many options we can choose from for our input parameters. In this case, I'm going to use a number parameter for our first item, which is going to be the length of the polygon sides of our Tensegrity. So that's it. Now we can see the arguments that this function requires. And the first one, of course, it is the name of the parameter, then the nickname, then the description, and finally the parameter access type, which can be an item, a list, or a tree. And as you can see, this is very similar to what we already saw with the C# scripting components of Grasshopper. Then we also need this other number parameter in order to define the length of our struct elements. And we also need two additional parameters to define the number of levels of our Tensegrity structure and the number of sides of our polygons, which are going to be, of course, integer parameters. And finally, we are going to define another parameter to specify the pre-stress force that we are going to apply to the cables of our Tensegrity structure. And we are not going to use this option, but it could be possible to define some of these input parameters as optional, so that, let's say, our Grasshopper component can be executed even if some of these parameters are not provided. Well, actually, what we are going to do is to define now this pre-stress force as optional, because we don't want to apply it for the first time that we define our component. So now what we have to do is to specify the index of this parameter. In this case, it could be 0, 1, 2, 3, and 4. Like that. Okay, and now we have to write our output parameters. So this is the one that our template gave us by default. So we are going to delete it. And instead, we are going to use first line parameter, which is going to be the cables related to our polygons, let's say. So the horizontal cables, so in other words. So what we are going to do is to set our parameter this way. So the name is poly, and then the nickname is this p, and then this is the description of this parameter, and this is going to be a list, in this case a list of lines. Okay, so let's copy this parameter for the next ones. So now what we need is another output parameter for our vertical cables. So in this case, let's name them bracing, and this is going to be a B, and bracing cables, like that. Then let's move on. Of course, since this is a Tensegrity, we also need our strut elements. So basically, this is going to be struts, str, and strut elements. And finally, let's specify the supports for our Tensegrity structure. And of course, this needs to be a point parameter, then supports, and basically support point. So now we are going to jump into the solve instance method, and this is a method in which we are going to define the behavior of our Grasshopper component. So basically, what our Grasshopper component is going to do. So here we can see that we are getting this script that we are getting by default with our template or with our extension. So let's put this down now. And basically the first thing we need to do is, as we can see, to assign the input parameters. Because if you remember, in the Grasshopper scripting components, we already had those parameters as arguments for our method or function, but we are not getting those, let's say, parameters as arguments anymore. So in order to get those parameters, first, of course, we need some variables to be able to assign those parameters into something. So let's do that. And of course, these variables, or rather the data types of these variables, have to match, of course, the parameter types that we define here for our input parameters. So for instance, the site length has to be, in this case, a double, because we define a number parameter here. So you can see that we have these variables here: site length, strat length, level count, vertex count, and pre-stress, which are basically the same as our input parameters here. So we are not going to be using the pre-stress now, because we are just going to focus on the geometry of our tensegrity, but let's define this value anyway. So okay, those are our input variables, but we have to actually assign the parameter values into these variables. And we are going to do that with this getData function. So what we are doing here, let's forget this for a second. So we're going to use this data access argument in order to assign those parameters. So we are going to call that argument, and then we are going to use the method getData. And we have to say, okay, so for the first parameter, in this case, of course, the parameter with index 0, we are going to get the data, and we are going to assign it by reference to the site length, because this is our first parameter, and then this is the second, the third, and so on and so forth. So let's take this variable, and that's the way to go. But let's take a look at the values that we got by default. So basically, what they are doing here is not just calling this method, but they are using it inside of a conditional structure, and let's do the same. So what they are saying is, okay, we are going to call this method, and if we get no answer, which happens if no input parameters is provided, then we are going to return, or basically to exit this solve instance method. Okay, return, it's not going to return any value because this is a void method, which means that it's just going to finish our program in case that no input parameter is provided. So this is a good practice actually to define our methods of assigning the input parameters inside of this conditional structure. Okay, so let's do the same for the other input parameters. So that was the first, then we need to define the strat length, and let's move on, and then the next parameter is going to be assigned into this variable, and we're almost done. Actually, we're not going to define it because we will not be providing the pre-stress force, so let's leave it like that. Okay, so let's move on. The next step, it says here, now we should validate the data and warn the user if invalid data is supplied. So let's skip this step for 1 second, let's say. And now finally is when we are set to, well, it says to create the spiral or to create our geometry in this case. So basically in the example, they do it with a separate function, which is outside of this solve instance method. But they did this way because they just have one curve as output parameter. So their definition is more simple that way, let's say. But in our case, we are going to have several different output parameters. So in my opinion, it's easier for us if we define our script completely inside of this solve instance method. So let's delete this function, and we are set to create, in this case, the Tensegrity structure. Okay, here we go. So the first thing that we have to do, as we already said, is of course to spell the words right, and then to define our, let's say, mathematical parameters that govern the definition of the Tensegrity structure. So let's go for it. I'm just going to copy it because I think it's faster that way. So first we need the number of levels, as we say, and that's just, or rather the number of planes, and that's just the number of levels plus 1, that's easy. Then we need our angle theta that we got from that formula, if you remember, which was optimizing this angle so that we get more stability and less stresses. And then we need the radius. This is basic trigonometry, no big deal here. And finally, we are going to get this height as this square root, which we already saw. So if we think for 1 second, we can see that we are calculating a square root here. And of course, if you remember the basic concepts of mathematical operations, the content of our square root has to be always a positive value. So otherwise, if this is not positive, it means that our program will crash. So this is the check that we are going to do actually. So now we are ready to come back here. We have to do this check after we define these parameters here, otherwise we are getting an error here because they were not defined. So if you take a look, the thing is that the length of our struct elements, or red lines, if you remember from our explanation, they need to be bigger than these values here, otherwise we would get a negative value, and the let's say the geometrical definition of the tensegrity would not be possible. So anyway, if this overall value is negative, it means that our struct elements need to be longer. So let's display that message: struct elements need to be longer. And of course, this happens if the radius of our polygons is, let's say, much higher than the length of our struct elements. In order to do this check, we need these parameters here, and we want to do that in order to avoid our program from crashing with this operation. So actually, we should have to define this check somewhere in the middle, like that. Okay, so let's move on, and this is our, let's say, main content of our of our method. So basically, this is the subroutine that we want to write. So first, we still need to define this phi angle, which is key for the definition of our tensegrity, as we already explained. And now we are ready to define the nodes of our tensegrity as point objects, so that the output elements or output parameters are defined but by just connecting those nodes. So we are going to define those nodes not as a list but as a tree of point objects. So this is a data tree of point 3D objects. So okay, it seems right, but now I am getting an error. Well, of course, I have to use the new keyword because I'm initializing a new object, and I am getting an error, and I guess that this is because I'm not referencing the library that contains the data trees. So let's click here to see what solutions it is suggesting using Grasshopper. That sounds right, because of course data tree is inside of the Grasshopper library, and we have to call it in order to use that content, of course. So let's try that, and now we can see that we don't have that error anymore. Okay, so now let's actually define our tree. Let's say 4. So let's say for I is 0, that's right. And this is going to be smaller than the number of levels, or planes rather, because now we are thinking in an horizontal way. Let's say this, inside of this loop we are going to define the points of each level, and we are going to assign them to a tree. And if you remember, in order to add new content into a tree, we need to specify the path of the branch in which we are going to define those objects, or we are going to add those objects. So let's define this path as new, that is a Grasshopper path, and now we have to specify here the index, or rather the address of this particular branch, and in this case we are going to use just this integer that we are getting from this loop. So basically this is the easiest way of defining, or just of defining a path for the branches of our tree structure. So let's see what Visual Studio has to say for that. And of course we have to use this other library in order to avoid this error. So let's click here, and we can see that Visual Studio has automatically added this library here, this one here. So now if we get back to our script, we can see that there are no errors anymore, at least here. So let's move on. And now we have to define the nodes in its polygon, let's say. So for that, we're going to use another loop. And of course, we cannot use the same variable, the same I variable again. So let's define this with the J letter, of course. And this is going to be smaller than the number of vertex of its polygon. Okay, so now let's define the coordinates of its point. So first let's start with x, and this is going to be of course the radius. Let's take the radius here, and we are going to multiply it by the cosinus of our of the angle of its node, let's say. So let's take this function here, that's right. And now the angle that we need to define, of course, it's the difference angle between its level, and that was theta. Where are you? That here. So as we move higher, this angle keeps increasing. So we have to multiply it by I, and then we have to add, let's say, the angle of the polygonal sector in which we are for its vertex here. And this is basically phi multiplied by j, like that. And that should be it. So now let's define y the same way. Well, of course, not the same way, because we have to use the sinus instead of the cosinus, like this. Okay, fine. And finally, of course, we need our c coordinate, and this is very easy because this is just going to be I multiplied by the height of its level. Okay, here, where are you? Sorry. Yes, here it is. Okay, it looks nice, and of course, finally, we need to add this point into our tree. Let's call my tree, and we are going to use the add method. And in Visual Studio you can see the possibilities that we have in terms of arguments. So this is the one that we are going to use. We are going to specify first the data that we are going to add, and then the path of the branch in which we are going to add these objects to. Okay, so first, the data that we are going to add, of course, is our new point, and the constructor of our point is x, y, z. Of course, you can take a look into the Rhinocommon documentation to review it. And now we need to specify our path. And I am getting an error because this is a point 3D. Okay, so now we are ready to start defining the elements that make up our Tensegrity. But before that, we need to define some variables so that these output parameters can take the value from some place. I mean, this is the same process as we already did with the input parameters, because you remember that we created these values so that we could assign the input parameters into something that we could use inside of our code. And now we have to do the reverse process, let's say, for our output parameters, which I remember that these are our output parameters. So let's start with our supports, let's say. So yes, supports, and this is going to be a list of points, and again, new list of points 3D, that's right. And let's define this. So the supports are going to be basically all the points that are on the lowest level of our tensegrity, which is basically the branch with index 0. So in order to do that, we can use a loop to assign those points into this new list. So let's use a for each loop. Now I just press the tab key twice and Visual Studio autocompletes. So let's say for each node, I mean, it doesn't matter how we call it. In nodes, I mean nodes, of course, but the nodes are the, let's call the data tree, and then we need the branch with index 0, let's say. So, okay, I mean, here we could specify a Grasshopper path, but since it just have one number or what identifier, let's say, we can directly use the integer as an index, and Visual Studio or Grasshopper automatically converts it into a Grasshopper path. That's also a cast process, as we already saw at the beginning of this course. So anyway, let's move on. And now for each node, what we are going to say is, okay, supports, sorry for that, supports add, and this is a possibility. I mean, and another possibility, of course, would have been to just define our supports this way, because this is exactly, I mean, this is already a list of points, so that could have been another option, but let's stick with this definition for later on. And so we already have our supports, and now we also need our bracing elements and polygonal elements, so I mean cables, and then we also need our strut elements. So all of them are basically lines. So let's start with our strut elements. Struts, this is a list of lines, like, sorry, that's right, and of course this is a new list, and we do the same for our cables. So let's say poly cables and bracing cables. Okay, here we go. And now we have to go through this tree again in order to define our elements. So let's just copy this definition of these loops. So that's right, and those are my levels, and these are the vertices in each level. And of course, let's close those loops like that. And now we have to define, let's say, 2 consecutive nodes of each polygon. So this is easy because we are selecting its node of the polygon, let's say. And if you remember, we are getting a list with this method, and with these brackets we are just getting any particular item of this list. So this is easy to understand, and now we have to define the next node, so that we are defining here, let's say, the polygonal cables. So now we have to define the next node, and I'm using this, let's say, exchange command here. And the reason for that is, okay, we could use the index, let's say, j+1 to get the next node, but imagine if we reach the last node or the last vertex of our polygon. Then what we would have to do is to get the first index of the list, so that the polygon side, or the cable in this case, goes from the last point to the first one. And with this command, this is basically the reminder. and it means that if j, it's basically, remember that we are in the end of, at the end of the list, so j plus 1 would be just 1, or would be just exactly the same as vertex count. So with this command here, we would get 0 if we are at the end of the list. And if we're in the middle, it doesn't matter, because the remainder, if this number is lower than vertex count, it could return just this number. But this is basic mathematical operations. And now let's define our baseline for our just for our cable. I mean, let's define our cable this way, which basically with a line connecting the node A and node B. And now we just have to add this line into our list of polygonal cables, like that. Okay, and now we have to define our strut elements and, let's say, bracing cables. And if you remember our geometrical definition, we basically have one level more than vertical elements, because if we have just a tensegrity of with one level, let's say, we have two planes and one family of vertical elements. So what I'm trying to say is that we have to specify if j is lower than the, actually not j but I, I'm sorry, because this is the variable that we are using to loop through all of our levels. If this is lower than number of levels, then we can go on. Otherwise, we will get an error because we are not defining as many struts. Now we have to do exactly the same process, which is defining the two nodes that we are going to be connecting with our strut elements. And as you can see, there is an offset here because we are connecting the elements with the level above these nodes here. So this is the line that we are going to specify as our strut elements. And now let's just add this line into our list of strut elements. And now let's define finally our bracing cables. And here there is an offset, of course, between the levels and also between the vertices. Okay, so now we are going to define our baseline bracing cable baseline, bracing cable baseline as a new line between my two nodes, node E and node F. Like that. And again, let's add this new line into our list of bracing cables, and that should be it, I think. And yes, and finally we are going to assign, I mean not the spiral, but our tensegrity elements to the output parameters. So yes, okay, let's move this back, and yes, so basically we have to use similar functions as we did to get our input parameters, but now set data. But this is a bit tricky because now we are not dealing with single items as we already did with our input parameters, but we are dealing with our lists here. So what we have to do is to use, instead of this method, to use set data list. And the first output parameter, if you remember, were our polygon cables, so we have to keep the same order. That's important. So these are my polygonal cables, and then we also have our bracing cables, strut elements, and supports. Right, in that order. So let's assign those variables to those output parameters. So bracing cables, struts, and supports. Where are you? Here you are. And of course we have to use the right indexed. And we have seen that we have now these possibilities to deal with, let's say, list or tree structures for our output parameters, and we can do exactly the same for our input parameters. So imagine if we would be using lists instead of items, we should be using this other function, get data list, or even get data tree if that was the case. But we are dealing just with items, as we already said here, so everything is right. And now we are done with our solve instance method that, as we said, it's the method that describes the behavior or the action that our Grasshopper component is going to do. So now we are almost ready to test our Tensegrity component, but before that we have to take care of a couple of things. So first, the exposure of our component, let's say, and in this case is primary. We are going to leave it like that because we just have one component, but basically with this parameter we can control where our component is going to be in, let's say, the Grasshopper ribbon. So let me explain that with Grasshopper. So basically, if we come here, we see that our components are going to be sorted in alphabetical order, but we can use the exposure to control more or less where we want them to be located. So in this case, we can see that these two parameters, or containers in this case, are defined with exposure primary, let's say, and then we have these others with exposure secondary, and this could be tertiary, and this quaternary. So with this kind of exposure parameter, Grasshopper generates these kind of separators to control a bit where our components are going to be located. Okay, so let's leave it like that. And then, of course, we need our icons for our Grasshopper component. So how can we specify the icon for our component? So for that, we have to come to project, and then go to the properties of our project. Here we are. And now we have to come to resources, and it says this project does not contain a default resources file. Click here to create one. Okay, here we go. If you get an error in this part, it may be because you need to start Visual Studio as an administrator, which is very advisable if you are developing plugins for Grasshopper. Okay, anyway, imagine that everything goes right, like in my case. So now what you have to do is to come to add resource, and then you are not going to click here, but you are going to click into add existing file. I already have my icons here, and now I'm going to add the icon for my Tensegrity component, like that. So the icons, as you see, are basically images that are just 24 by 24 pixels, and it's good if you can save them as PNG images so that you can, let's say, erase the background and they look like nice transparent icons. So let's add this icon like that, and now we have to save this, and we can come back to the class of our component, and we can uncomment this command. Yes, we have to say using Tensegrity properties. So now Visual Studio has added this, let's say, command here to start using our resources that have been generated here. And now inside of our properties, let's say, so now we can come back here again, and let's say, of course, we are getting an error because there is no such icon inside of our project. But what we do have is our icon for our Tensegrity, which we have just imported. So that should be it for the icon. And finally, the last part is to generate a new git. So basically it is the identifier of our component, and you have to generate a new one each time that you are writing your own component. So for that, I like to come to this website, gitgenerator.com, and here we can just click on generate some gits, and we can take this and come back to our Visual Studio project, and we can just basically replace the git that we got by default.